For the past few years, a common working assumption in parts of the AI field was that chain of thought could serve as a window into reasoning. When a large language model solves a problem step by step, showing its work along the way, the hope was that this explanation reveals how the decision was formed. The logic flows from thought to decision. This assumption influenced a substantial body of interpretability and safety work. If you want the model to reason carefully, you train it to think carefully. If you want to understand what the model is doing, you read what it writes. Chain of thought became a key part of how researchers approached reasoning transparency. But in 2026, a team published evidence that challenged this picture. The question sounds simple. When a reasoning model decides to use a tool, to call a function, to take an action, does it think first and then decide, or does it decide first and then think? For years, many researchers informally assumed the first. The thinking would happen in the hidden layers, but the chain of thought would reveal at least part of how the decision was formed. But what if the decision was already made? What if, by the time the model started writing its explanation, the choice was already encoded in the model's internal activations, hidden away in a space where language doesn't touch? To find out, you'd need a way to read what's buried inside. Enter the linear probe. Think of it like this. Imagine a radiologist training a very simple diagnostic tool. Not a full MRI, something much simpler. You feed it examples of the model's internal state paired with the choices the model makes, and it learns a simple linear pattern that separates one choice from another. The probe doesn't understand the whole computation, it just finds a simple direction in activation space that is predictive of what comes next. That's the power of the linear probe. Its simplicity is exactly what makes the result so striking. Sakiveli Sakiraja and co-authors set out to test this. Using linear probes, they looked at the model's internal activations before the model had generated a single reasoning token. Can we decode what the model is going to choose just by looking at these hidden states? The answer was yes. With very high confidence, the probes could often predict which tool the model was about to call. In some cases, the decision was detectable before any reasoning step had been written. Then came the hard part. They didn't just detect the decision, they manipulated it. Using activation steering, researchers add a small perturbation to the model's internal activations at the chosen layer. Think of it like a puppeteer, who doesn't pull the limbs directly but shifts the puppet's balance before it moves. The model still runs normally, but the intervention nudges its internal state toward one option or another. In this case, the perturbation is derived from a probe identified direction that correlates strongly with the model's choice. If changing that signal changes the behavior, it suggests the signal is not just predictive, but behaviorally relevant. They asked, if we nudge this signal, does the model's behavior change? It did. Depending on the model and benchmark, steering flipped behavior in roughly 7 to 79% of cases. The model would choose a different tool, take a different action. But here's where it gets eerie. When the steering changed the decision, the chain of thought reasoning changed too. The model didn't resist. It didn't say, wait, my hidden activations are telling me one thing, but my reasoning suggests another. No, in those settings, the chain of thought often rationalized the changed decision rather than resisting it. It acted as if the new decision had been the right one all along. The reasoning caught up, it adapted, it justified. Before we go further, we need to talk about alignment. Alignment is the goal of making AI systems do what we actually want them to do. Not what they claim to do, not what looks good on paper, but what they actually do. Some safety and transparency approaches rely on the idea that verbalized reasoning can provide useful evidence about a model's internal process. The logic seems obvious. Think carefully about doing the right thing, and you'll do the right thing. Show your reasoning, and we can verify it's sound. But Sakiraja's result challenges that assumption, especially for settings where models choose actions such as tool calls. The paper studies tool calling decisions, not deception. But it raises a broader concern. If decision-relevant information can be encoded before reasoning appears, then in higher stakes settings, the same pattern could matter for alignment too. Imagine training a model to be honest by rewarding careful, truthful-sounding reasoning. If the decision comes first and the reasoning adapts afterward, then in some cases the model's explanation may improve more than the underlying choice. The paper does not show that this is happening in deception tasks, but it does show a mechanism that makes the concern harder to dismiss. This raises a broader question. In some cases, training or evaluating a model through its verbalized reasoning may improve the explanation more than the underlying decision process. Some recent interpretability and oversight work treated chain of thought as a useful object for interpretability and oversight. Probe the chain of thought, trace the logic, identify which concepts activate at which steps. A common hope was that if a model reasons more explicitly about honesty or harm, that reasoning may help make its behavior easier to supervise. If you want to know whether a model is considering harm, examine its reasoning traces. If you want to steer the model towards safer choices, modify the reasoning to be safer. Part of the recent interpretability agenda depended on this picture. Language reflects thought, thought drives decision. The Sakurai's result puts serious pressure on that picture. If important parts of the decision are encoded in activation space before the model writes, language-based analysis may miss them or recover them only imperfectly. Training the reasoning may sometimes change the justification more than the core choice, and steering the language may not reliably steer the underlying behavior. In some cases, it may mostly change the surface narrative. These results create a serious challenge for approaches that treat chain of thought as a reliable transparency signal. Researchers who build their careers on analyzing chain of thought now have to confront a possibility. They've been reading the model's rationalization, not its reasoning. The X-ray machine they were using was pointed at the wrong part of the body. These results raise the possibility that some analysis of chain of thought capture post hoc explanation more than causal decision making. So what comes next? If decisions live in activation space, how do we interpret them? The paper itself points toward tools. Linear probes can detect decision directions. Activation steering can manipulate them. But this is a beginning, not a solution. There is growing interest in activation-based methods alongside language-based analysis. Sparse autoencoders, a technique that tries to learn a more interpretable sparse basis in neural network activations, are being applied to understand what models compute internally. Instead of mixed signals across many neurons, researchers can sometimes find more interpretable structure that correlates with specific concepts or behaviors. Groups like Anthropic have shown this can work for some transformer models, revealing features that seem to correspond to concrete ideas or patterns the model has learned. Circuit analysis, mechanistic interpretability, activation patching, and causal tracing. These may become some of the most important tools in the next phase of interpretability. Not analyzing what the model writes, but analyzing the geometry of what it computes. The new question isn't what is the model saying, it's what is the model doing. And in that space, language is not a window, it's a veil. We're moving from reading the model's autobiography to examining its blueprint. Every field has these moments, a moment when an assumption that held for years suddenly breaks, and researchers realize they have to rebuild. This could turn out to be an important moment for interpretability. If this result holds up and generalizes, it could mark the beginning of a broader shift. The field may be moving beyond treating chain of thought as the whole story. For years we asked the models to show their work and believed what they wrote, and we're learning that in at least some important cases, the reasoning we see may be partly post hoc rationalization, rather than a faithful account of the decision process. This has enormous implications, at least for the kinds of action selection tasks studied here. For safety, if you are trying to make a model safer through reasoning supervision alone, you may be improving the model's rationalization more than its underlying decision process. A safer sounding explanation is not necessarily a safer model. For evaluation, in some cases, examining the reasoning steps may tell you more about the model's explanation than about the causal path behind its answer. For deployment, if you're trusting a model because its explanation looks reasonable, you might be trusting a very good storyteller. The next era of AI interpretability will likely combine reading what models write with studying what their internal computations encode. It will be harder. It will be less intuitive. You can't just read a chain of thought and understand the model. You have to learn the geometry of activation space, but it will be more honest. These methods may let us get closer to the computations that shape the model's behavior rather than relying only on its verbalizing.